Okay, we have two periods today. We are going to go through chapter 5 of Emaths. We're going to finish the whole thing today, okay? We'll finish it off. So we have finished there's a Emaths chapter, I don't know what the one on polynomials, right? Today we're going to finish on Emaths, right? So chapter 5 of Emaths is on mainly graphs, okay? Specifically graph of this form, ax to the power n, where a is a constant, a number, okay, and n is also another number. So the variable here is x. Alright, now compare this with what you learn in Emaths. You learn exponential graph. Now exponential graph, this word exponent refers to index or power, okay? That is why your graph, for example, y equals e to the power x, right? The power is actually the variable. So as x changes, this will get exponentially large. So I hope you still remember how the graph looks like. This is x, this is y. Let's say this is y equals e to the power x. This is how it looks like. And when x equals to 0, anything to the power 0 is 1. This will be 1. Okay? If I have y equals to 2 to the power ex, when x equals 0, this will be 1 times 2. So the graph will look like that. And so on and so forth. Okay? And when I have y equals to minus ex, what I will have is a graph that is flipped over the x-axis. That means this x-axis is like the line of symmetry. Alright, so I have something like this. Again, the y-intercept is at 1 minus 1 here. It's a flip side of this, like mirror image. Similarly, for y equals to minus 2e to the power x. Okay. Now, what if x is negative? Then, if you can remember, it is this. It's a decay. This is a growth. As time passes by, things increases exponentially, like the virus now. Okay. But of course, if you are representing this as the virus, then time cannot be negative, so you don't draw this part. Okay, for this part is a decay. Again, for real-world application, you don't draw this part because time cannot be negative. Alright, so look at the context of the question. So this is just a recap of what you have done in Emaths. Okay, actually Emaths, you are supposed to know these as well, but you don't use e. We use numbers like maybe 2 to the power x, but the shape of the graph is the same, okay? So this is a positive, right? So you'll be going like this, passing through 1. But if there is a number, let's say 4 here, 4 times this, then this will be 4. Alright, if it is a minus here, then you'll be this. Okay, so I hope you can just go back and recall what you have learned for exponential graph. You're expected to know this in Emaths as well, but they won't really use e, they will use numbers like 2 or some other numbers. Okay, and perhaps also for the purpose of Emaths, go back and revise what happens when this number here, let's say I call this y equals a to the power of x. If this number here is between 0 and, that means less than 0 but greater than 1, how will the shape look like? Will it still be the same? Let's say 0.4x. Would it be this way or this way? Okay, so go back and review this. Okay, now we'll start Emaths. Now Emaths is very simple. We'll start with the most basic graph. Let's say you have x equals to 1. How does this graph look like? X equals to 1 would just be like that. Okay, x equals to 2, x equals to 3, x equals to 4, x equals to 5, x equals to 6, x equals to minus 1, minus 2, minus 3, minus. So these are all the vertical lines, okay, where you have x equals to a number a, meaning to say that all these are vertical lines. Okay, but if you have y equals to, let's say, 1, then you have horizontal lines. So this is y equal 1, y equal 2, y equal 3, y equals 4, so on and so forth. Okay, so I think this you are clear. Next thing you need to know is second thing. If I have y equals to mx plus c, okay, graphs of this form, you know it's a straight line, okay, but it's not vertical or horizontal. It has a slope because of this m here. So example is y equals 2x minus 4, intercept is minus 4, so you cut at minus 4, positive gradient to go this way. Y equals 2x minus 4. Now, what happens if I change the gradient to negative? Then it will simply be the flip side. Okay, it will just have a negative gradient, but it will cut at minus 4 as the y-intercept, same as what you have learned previously. Okay, now the third thing you need to know are graphs of this form. Okay, you learn it in Sec 2. Okay, of course there could be some other stuff here, but the general shape is this. If A is positive, the curve would look like this. Sorry, you will pass through the origin because there's no intercept. But if you have, let's say this is y equals to x squared. If you have y equals x squared plus 2, then you will cut, intercept will be 2. Alright, so all these are very, very simple stuff. But if A is negative, the graph will just flip over the x-axis. Same here for the other one, minus x minus 2. Okay, so you just flip over minus x squared minus 2. Okay, now what happens if I have this type of equation? Now we're going to the fourth type already. Y equals to x cubed. This is something you learn in Sec 3. So it's very simple. Sec 1 power 1, Sec 2 power 2, Sec 3 power 3. Of course there can be other stuff here, but let's just learn the general shape. Remember, okay, so this is like y equals to ax cubed. Okay, a is a constant. It can be negative or positive. So let's say I talk about a being positive. Remember, when your gradient for a linear graph is positive, it goes this way, right? It increases as x increases, y increases as x increases. Something like positive gradient this way, this way, right, going up. When a gradient is negative, it goes down, right? So think of it as the same thing, except that you have a curve. Okay? And because the intercept is 0, there's no intercept, right? Plus 0. So you will pass through the origin and then you will turn this way again. So this is the general shape of a curve of this form. Let's say y equals to x cubed. It looks like that. Okay? How about if your a is negative, meaning y equal minus x cubed. Very simple. Whenever you have a minus here as a coefficient, the graph gets flipped over the x-axis. So what was previously negative is now positive. Okay, what was previously positive is now negative. So use this x as a mirror. Okay, then it's very easy for you to draw. So the shape is like that. If you have other numbers, let's say x cubed, let's say plus 2x plus 3, something like that, right? Then it will be a more pronounced turning point. So there'll be one turning point. Okay, I just anyhow draw. 2 turning point. All right, and of course the intercept is 3. Okay, the real graph may not look like that, but it will be a more pronounced turning point. This one is next time you will learn. Is actually not really turning point. Next time you will learn. But you just know that this is the shape. Okay. But can you see that when the coefficient of x squared is positive, it's still something like your positive gradient going up this way. Okay, now what if I have y equals to minus x cubed and something else, we don't know know what. Okay, how will it look like? It will be not going up this way, but you'll be coming down. Okay, coming down like what? Like this being flipped. Okay, so can you imagine this being flipped? Can you see? Okay, can. You imagine you flip this over, flip this over. So for example, I draw with more strength so they can see from the back. Can you see? It'll be like a roller coaster going downwards. This is like a roller coaster going upwards, right? So this will be the reverse, this way. Okay, again, this will be, what did I write here? Oh. Okay, let's say it's plus, let's say 2x plus 4, and then this will be 4. Okay, but can you see that it's like something like a negative gradient? Okay, so for this topic, you need to be able to sketch graphs, but it won't be this form. For this more complicated looking kind, like this, it will be on graph paper. So you will have points to guide you. So as you can see just now, you know, I anyhow scribble, anyhow draw. At higher level, beyond JC and all that, you will have to be able to sketch more accurately. But now no need, now you just know this. At most we give you is, okay, how to sketch this. Minus x cubed, then minus 2, like that. Okay, so you know that this is positive, right? This is this one. This negative means the roller coaster is coming down. Okay, coming down. But because you have a negative 2 here, that means your intercept is minus 2. It actually means that the whole graph is shifted down by 2 units. Everything is shifted down by 2 units. And that is how you end up with this as the final answer. With this being minus 2 your y-intercept. Alright, so I hope you understand this. Okay, so the fourth thing done. Next thing we're going to do is, okay, actually the fifth thing is your exponential graph. Exponential graph, but we already done that in A-Maths. You just go and revise. Okay, now the very last thing we are doing is the climax of this first part of the lesson. Now this first part of the lesson is simply on graph. We will have a few parts to today's lesson, chapter 5. Okay, the first part is I'm doing graphs. Okay, how to sketch graphs. The second part I will do, actually I've secretly done with you in January already, so actually you know, but I think some of you still don't know, or maybe you forgot, so I'll revise later. It's called gradient of a curve. Okay, gradient of a line, you know, right? Gradient of a curve, I think you can remember, it's something like drawing a tangent to the curve and then you find the gradient. Okay, so that's what we are doing. First, second. Okay, the third one is real life applications of curves. And this part, I want to focus on 2 things. The first one is speed time, distance time graph. Acceleration time, not that commonly tested, but I'll still touch on it. Okay, the other one I want to go through is the shape of graphs. In real life. Okay, different contexts, under different contexts. Yeah, so these are the 4 things that I'll cover today, and that's it. Okay, now the last part of this first section is what we call reciprocal graphs. Okay, now remember that under exponential function, we learned that, if I have y equals to 4 to the power x, right? It's going to increase exponentially like that. Okay, this one, and this x-axis is what we call the asymptote. with this equation. Why is it called asymptote? Because this curve is going to go closer and closer and closer and closer to the to the x-axis, but it's never going to ever touch it. Okay, it's never ever going to touch it. All right. So this x-axis is called the asymptote to the curve. And similarly, if I have this curve, it is the asymptote to this y equals to 4 to the power minus x as well. Alright, you need to know this concept of asymptote because for reciprocal graphs, there's not only one asymptote. They see there's only one asymptote here, right? This is not asymptote, right? Because this curve actually cut this y-axis, right? So y-axis is not it's not an asymptote. The curve actually cut the y-axis. The x-axis is the one that's an asymptote. Alright, because you can't touch this. There's a song, you can't touch this. Okay, reciprocal graph. Reciprocal graphs, you can think of it this way. Reciprocal graphs, it will either look like that, like that. Okay, wait, this one is not very well drawn. Okay, not well drawn. Okay, it will either be made up of these, or these. Either two out of these four. That means, I show you one example. Let's say now I ask you to sketch y equals to 1 over x. Now, how do we sketch this? Okay, there's nothing to memorize. You use common sense. You see all those things just now, it's actually just common sense. All these are just common sense. Don't go and memorize like it's some difficult stuff. No, it's actually very simple. Okay, think about it. Can x be equals to 0? Can you sub x equals to 0 here? Let's say you want to come up with a table of values with this. Can you sub in x here? If I try, I press calculator, 1 divided by 0 is, they say error. Okay, so you cannot divide any number by 0. It's not defined. Okay, so you can't do that. Meaning to say that this y-axis is an asymptote. Okay, you cannot touch this. The line will go nearer and nearer and nearer and nearer to it, but you will never ever touch this. What do I mean by nearer and nearer and nearer? So now you know you cannot have x equals 0, right? Then we choose a number 0.00001, okay, or 0.00001, 2, 3, 4, 5. Okay, like that. You take 1 divided by this, it will be very, 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 very big number. That's why it's so high up there. Okay, of course I cannot draw all the way to my table there, but it will be a very, very, very big y value. Okay, when x is 0.001. Okay, if you slowly increase, let's say 0.01, then it'll be 100. Okay, 100, then it will be maybe somewhere here. Then you slowly increase again, 0.1, then be 10. So you can see that the graph will get nearer and nearer as you increase the x values. As you increase the x values, you get nearer and nearer and nearer, something like your exponential graph. So again, this is your asymptote. Okay, so let me repeat. When x is positive, okay, when you sub in a positive x value, x is positive is here, right? X is positive here, x is negative here, right? When x is positive, your y will definitely be positive because this number is a positive number. So this will be your graph here. Okay, let me redraw. This one is it will be like that. Okay, but how about when x is negative? When x is negative, let's say minus 0.1 and all that, you will find that y will be negative. Overall, y will be negative. So it's this portion, right? And if you were to sub in some values to try and all that, you will find that, okay, sorry, it should look symmetrical, meaning it should look like that. If I'm like that, you should be like that, symmetrical, okay? So the line of symmetry, if you want to know what is the line of symmetry like, it is somewhere around here, okay? It is a line that is, sorry, I can't find my ruler, never mind. It is somewhere around here. The mirror line is somewhere around here, okay? Yeah. So this is your graph y equals to 1 over x. Now, how about y equals to, let's say now I put y minus 1 over x. Okay, let's think. When x is positive is this way, right? X is positive. What would my y be? My y overall would be negative. Okay, so y will be negative. That means, okay, don't draw like what I draw, I'm just showing you. That means my curve will be this way. Again, going closer and closer and closer to my x-axis, but never touching it. Going closer and closer and closer to my y-axis, but never touching it. Alright, now what about if x is negative this way, right? X is negative this way, x is negative, negative times negative is positive. Overall, my y values will all be positive. So the curve will be here. Okay. So these two, the red ones, the red curves, make up this curve. The black one, the black curves, right, make up this. Okay, so you'll find that, when you're asked to draw this kind of reciprocal graphs, why is it called reciprocal graph? Because it's something like, your y equals to x, and then you flip it over. Reciprocal means flip. Like I reciprocate your love for me, then I return you, I show you back. You reciprocate your parents' love for you, then you show them back the love that they show you. Okay, so that is what they mean. So reciprocal of this, reciprocal of 4 is 1 over 4. Reciprocal of x is 1 over x. So all these are called reciprocal graphs because you see they flip the x to the denominator. Okay, yeah. So that is for this first part here. How about this? There's another kind of reciprocal graph. I give you a simple one. Sketch y equals to 1 over x squared. Now, how do I sketch this? Again, you will find that I cannot sub x equals to 0. Cannot. Okay? Why cannot? Because again, it's 1 divided by 0. Alright? And you will find that the other thing you need to realize, just now I didn't mention, is as the this one cannot, right? Cannot. Okay. As the value of x increases, you sub in all the big values, right? You sub in this one, 1 million. Okay, this whole thing will become very small. Then you sub in 3 billion or 10 billion. It will become even very smaller. But overall, talk about this whole number, this y value, it will never reach 0. So again, it's like your exponential graph. It will look like that. You go nearer and nearer, but you will never cut. Okay, how come it didn't cut through here like your exponential graph? Remember your exponential graph, they cut through. They cut through like that. Then this is the asymptote, then they cut through. Then this is maybe 1 for this case. Okay, why didn't it cut through? Because your x in this case, your x in this case can be 0. But the x in this case, right, cannot be 0. You cannot divide any number by 0. That's why it actually want to cut, but sorry, cannot cut. So it can only go nearer and nearer and nearer and nearer and nearer. Why is it going nearer and nearer and nearer and nearer and nearer? Because when this number gets smaller and smaller and smaller, I'm talking about denominator, smaller and smaller and smaller and smaller and smaller, then you power it to 2. This whole overall number, right, get bigger and bigger and bigger and bigger and bigger. That's why it goes all the way up. Okay, so I hope you understand that for reciprocal graphs, this is also a reciprocal graph. Why? Because x squared is at the denominator. Alright. The way I phrase it may confuse you. What I mean is when you are talking about positive index, most of the time, you know, in the exam we want to test whether you know your indices well. We may not write it like that. We may write it like that. Okay. Then we ask you to sketch this. Or we may put some number here. Okay, you yourself must know that, oh, actually this is this reciprocal graph. Okay, it's always easier to see positive index than negative index. That's why we always ask you to leave your answers in positive index. Okay, so you yourself must know, and you must change it to positive index. Then you will know that, oh, actually this is also a reciprocal graph. Okay, now what's the difference between this reciprocal graph and the one we saw earlier? Let's take a look at the one we saw earlier. How would I sketch this? Let's say I have 2 over x versus minus 2 over x. We did that just now with the 1 and the 1 minus 1 here, right? What if it's a 2? It's the same shape. It's the same shape. Okay, later I will put them together and then let you compare. But we mentioned just now, right? When x is positive, that means here, my overall y will be positive, right? So the graph will be here. Okay, don't put the ticks in your working. I'm just trying to tell you it's this quadrant. There's actually, you know, the coordinate, this scale is divided into 1, 2, 3, 4 quadrants, right? 1, 2, 3. Okay, 1, 2, 3, 4. Okay, I'm talking about when this is x positive, this whole thing is positive. So positive x, positive y, so it's this quadrant. Okay, now let's say x is negative now. X is negative. So you always think when x is positive, what's the y? Y positive or this quadrant? So it's like that. When x is negative here, when x is negative, okay, your y overall will be negative, right? Y will be negative, maybe minus 1 or minus 2. Okay, we here. Oh, so is this quadrant. Then you draw here. Okay. Now, what's the difference between just now what we have drawn, y equals 1 over x, and y equals 2 over x? Okay, again, like what I mentioned to you when we were discussing exponential graph, right? You always sub in simple, small number, manageable number if you don't know lah. Okay, so if x is 1, in this case is 2, right? Okay, so it is 2, so this must be 2, 1, 2, right? How about this? When x is 1, 1 divided by 1 is 1. Oh, it is lower. Okay, which means this graph is lower than this fella. Alright, so if you are asked in exam questions to draw on the same graph or same scale, that means they want you to draw on this same x and y axis. Then you have to draw them together, and you have to know that one of them is lower than the other. Okay, so use simple numbers to guide you. Very simple. Okay, that's all. Now, oh, we have not finished this question. Sorry, I diverted. But I need to show you this first. Then we come back to this. Okay, what if it's a minus 2 over x? Again, you think about it. When x is positive, okay, x is positive means it can either, the y value can either be here or here, right? cannot be here, right? Okay, cannot be here. This is x negative, okay? So when x is positive, it's either this quadrant or this quadrant. So when x is positive, overall, it'll be negative. The y value will be negative, so it'll be here, this quadrant. Okay, now think about it. When x is negative, then here negative, so they will overall be positive. When x is negative, it can either be this quadrant or this quadrant, cannot be here. Your y will be positive, so it is here. Yeah, so that is your y equals to, let's say 1 over x. We keep things simple, and this y equals to minus 1 over x. We keep things simple. I just want you to compare with this. Okay, now what if I have y equals 1 over x squared? Now the good thing is this, when you see x squared, right, whether x is positive or negative, the y value will be positive. So this is how the graph will look like. That's all. Meaning to say that if I ask you to sketch y equals to 1 over x squared, this is how it looks. Because no matter what x value I put in, it can be plus million, plus 2 billion, plus 1, plus 2, or it can be minus whatever number, overall is positive. Okay, so this is your, this 2 is your y equals 1 over x squared. Can x be 0? Cannot. That's why this is an asymptote, this is an asymptote. Now, if you know this, then I ask you to sketch this. Okay, common sense would tell you, based on whatever you learn in Sec 1, Sec 2, common sense would tell you that it's just a flip side of this, right? You just need to flip the graph over and you will end up with this. Yeah, that's all. Okay, but let me just show you that this is true. Okay, sorry, I wanted to put a negative here. Okay, there's a negative here. This is positive. 1 over x squared, this is negative. Okay, why is it this shape? Because whatever x value I put in, whether plus or minus, overall this will be positive. Okay, overall this will be positive, but overall this will be negative. So it will always be in the negative region. That's all. Okay, now of course in the exam question we sometimes try to, not say sometimes, most of the time we try to make it more challenging for you. So what we do is we give you 1 point like that. We put here 1, 1. We tell you that this point is 1, 1. Okay, they will put a dot here for you. Alright, then we ask you to sketch y equals to 1 over x squared. Then how do you do that? Okay, if you were to draw it this way, you know that, oh, whatever x value I put in, it will be positive, right? So you know that it's going to be like that and like that. Whatever x value I put in, whether positive or negative, the whole thing is positive. So it will just be like that and like that. That's all. Without touching the asymptote here, without touching, it's just going closer and closer. So if you draw it this way, right, then you get 0. The teacher will mark you wrong and give you 0. Why? Because they especially put the 1, 1 here because they want you to tell them whether your graph will pass through this point. Okay, so you have to sub in, not both values, not both. You sub in x equals to 1. Alright, then you show them that, oh, when x equals to 1, my y is also 1. So 1, 1. 1, 1 lies on my curve, which means that the correct answer should be you drawing a curve passing through this point before you move towards the asymptote. Sorry, this graph is a terrible graph. It should be a curve. Okay, then this other side you just follow. Try to be as symmetrical as possible. Alright, and then moving closer and closer, but do not touch. Do not touch the x and the y axis. x and y axis. Okay, so that is one way they can test you in the exam. Alright. Now, is there any other way they can test you? Yeah, maybe they can ask you this 1 over no, minus 1 over x squared, then minus 2. Then how do you draw this? Okay, so for those of you who are not very sure, sorry, what x squared, I meant it to be x squared. Those of you who are not very sure, you can draw the basic form first. Alright, you can ignore this first. That means you draw what you know first using dotted lines. After that, you can erase something like that, right? So this is your y equals to minus 1 over x squared. Okay, this minus 2 simply means the whole y value is shifted down by 2. Okay, so instead of this x-axis being the asymptote, it no longer is the asymptote now because you are now shifting everything down. So you have to draw a dotted line. It must be drawn. You cannot just assume that the examiner know that you know. And then label this, because you shifted down 2 values, right? 2 units. So you label this, and then you draw your curve going closer and closer and closer to this. Draw your curve going closer and closer and closer and closer to this. Yeah, so that is your y equals to minus 1 over x squared minus 2. Okay. Now, there is a more challenging question in your homework. You can try it out if you wish to. If you don't wish to, then we will do it another day. I think we'll do it another day. We'll see how first. Okay, so that's the end. That's the end of our sketching of curve, sketching of graph. Okay. How much time have I left? Oh, it's about 36 minutes gone. Okay, gradient of a curve. Oh, you have done this before already. Wait, okay, remember some time ago we did something like that. Ask you to draw a graph. Can you see? Okay, you can see. Ask you to draw a graph, and then I ask you to maybe find gradient of curve at point 1, 2. So what must you do? I'm now telling you the by right way. By right. You are supposed to locate the point on your graph or on your curve. Locate the point. Okay. Then use your ruler. Let's say this is your ruler. Roughly see. Oh, okay. Cannot be like that, right? Cannot be like that, because when it's like that, your tangent. You're supposed to draw a tangent. Tangent only touches one point on the curve. So this is a tangent. This is a tangent. This is a tangent. This is not a tangent because it cuts 2 points already. Okay, this is not, this is not, this is not, this is not. So a tangent is like something like you drop this down, and then it simply balances here very nicely with the spacing here more or less equal to the spacing here. Okay, and without touching any other part of the curve. All right. Once you have drawn this line. Okay, you see carefully. Anyway, this is your textbook, page 141. 141 textbook. Question, I don't know what, it doesn't matter. Okay, then you draw this green line. Draw this green line, right? Okay, don't use the method shown in your textbook. Do not use this method. Don't use this method, okay? Use the method that I'm teaching you. Don't go and measure, don't bother. Okay, what you do is you find one coordinate here, and in this case it is using, this is 3.5. And okay, you can actually choose any other point on your tangent. But of course, the most accurate point you can ever have is the point that they already asked you to find the tangent at which this is the gradient is at. So what you want, right, is a very accurate point. So you use this 1, 2. So always use the point that's given to you and another convenient point. Alright, convenient point means a very nice number that you can read off easily from your graph. In my case, I just choose this point because it's 3.5. I don't want to choose a point, a weird point like this. Something point something, I don't want, okay? Yeah, but if you really cannot find, then you have to do it lah. Alright, you have to choose that point. Okay, after you have done this, right, you simply say m equals to, use this formula. Okay, if this is 0.1, then this will be x1, y1. If this is 0.2, then this will be x2, y2. Then you can just calculate your gradient to be whatever it is. Okay, most of the time you have to run off to 3SF. Now this is the by right, the correct way to do it. Okay, but as I mentioned, many of your graphs, you see, if you look at this graph, how smooth it is. Many of your graphs are not like that, you see. Many of your graphs cannot really make it. Okay, so if your graph cannot make it, this question is 2 marks. You will lose the 2 marks. You may maybe get 1 mark for your method. So important thing is you need to show this tangent. You need to choose 2 points on your graph and then you show this working. If everything is done in the proper manner, they may give you 1 out of 2 marks even though your answer is not accurate. But what I'm trying to show you, and actually I've shown you last time before, is to get the most accurate answer before you even draw the tangent. Alright, so please listen carefully. But this method, right, take note. I think some of you are very confused. I'm trying to help you, but you're actually confused about what to do. So I'm going to repeat what is to be done. Okay, now this is your side working. You don't show this here or whatever, or you want to show you want to write, you write in pencil. Okay, what do you write? You are given this curve, right? So this is the equation. I mean, you have drawn this curve already. So what do? You want to find the gradient at this point. What is this point? It is 2, so it is 1, 2, 1, 2. Okay, 1, 2, this point. Okay, so what I'm doing now, right, is I'm choosing a point. If I zoom into this point, right, if I zoom into this curve, you know, if I zoom into this curve, I zoom into this curve, what I will see is actually a straight line. I zoom in, zoom many times, I only see one straight line. Okay, so I'm going to make use of this principle to help me get the most accurate answer. Based on the fact that when you zoom in to this curve, right, very small part of it is actually a straight line. Okay, which means that for it to be a straight line, it must be a point here, on the curve, a point here on the curve, very close to the point 1, 2. Okay, so how do I choose a point that's very close to the point 1, 2? I have to choose a point that is maybe 1.001. I can choose 1.0001 also can, but I think this is good enough. Do you know how small this is? If I'm 1.001 cm from you, I'll be arrested by the police now under the COVID-19 law. Okay, so this is actually good enough already. Okay, so what I need to do now is, if this x value, right, is 1.001, and I lie on the curve, no, this point lies on the curve, this curve. Okay, then I must satisfy the curve equation, right? When I sub this in, I can get my y value. Okay, so what I do is, I type in the curve equation, which is 5 times what? 1.001, then I put bracket. Okay, then minus 1.001, then I square it and then I close bracket. Now that will give me my y value, right? And as you can see, the original point is 1 2. Okay, 1 2. The point that I want to be very, 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 very close to it, right, is 1.001 and 2.0014995. 2.0014995, right? Okay. Now, don't you agree that if I were to find the gradient for this, it will be the gradient of this line. Okay? And the gradient of this line actually is the gradient of this line. How come? Because you see, if now you have very good microscopic eyes, you zoom in here, right? You actually here, not even bigger than my pen tip. Okay? So you are here, you are actually parallel. This line is parallel to this tangent. Parallel. Okay? So this is the most accurate gradient you can get. Okay, now you notice how I pressed just now. I don't know whether you can see from the handphone. You can see, right? Okay. So this value, right, don't erase it. You see what I do in the exam, right? I write this in pencil, or later I just cancel it. You straight away y1 minus y2 divided by this over this. Okay. So I take this minus 2, then I press equals. Okay, that would be my y1 minus y2. Then I go and divide. I know the difference between these two is 0.001. I straight away press. Okay, I get this value. You don't go and write this there. You don't go and write 2999 over 2000 as your gradient answer. You get 0. They know that you use calculator. Okay, you press the equal. Sorry, you press the... what did I do? Okay, never mind. Okay, never mind, I repeat. I think I pressed wrongly. 2.0014995, right? Okay, I minus 2, that's y1 minus y2. Then you press equal, must press equal, because that's your whole value divided by the denominator value, which is... did I do correctly? Wait. Let me double check. Okay. Minus 2. That will be the y1 minus y2, right? Then you divide by 0.001, because that's the difference between this and this. If you don't know, then you just divide it by bracket this minus this. Then you get this, right? What I mean is you don't write this value here. Okay? Then you press, you change it to decimal. You get 1.4995. Oh, meaning is 1.5 lah. 1.5. Okay, if you were to look at this question, you see the textbook, right? When they work it out using this, they go and measure this length divided by this length, your rise over run. They also got 1.5. That means this is the most accurate answer you can ever have. Okay, so without doing the tangent thing, you really know the answer. Now, what do you do with this answer? You cannot. Some of you hand in your chapter 1 work, and then you show this working. You show this working, and then you end up with this answer. Okay, you cannot do that. You do that, right? They really know that you are working backwards. Cannot. They want you to draw this tangent and then find the gradient based on this y1 minus y2 over x1 minus x2 formula. Okay, so you have to show them just show them. Okay, how do you show them? Okay, I'm going to tell you now how, so you listen carefully. You know that the answer you're working towards is 1.50, right, to 3SF. So what do? You wait, your final answer you don't write yet. I'm saying you're working towards this. Your answer may vary slightly from this based on what value you chose later. Okay, so how do you do it? You know that gradient is around 1.50. How do I get gradient 1.50. It must be the rise over the run. Rise over the run, rise divided by run must be equals to 1.50, right? So a good run to choose on your graph is 1. Okay, why? Because if I want 1.50, I just choose 1.50. Where is it? 1.50 right here. Okay, don't you agree that this triangle, the rise is 1.50, the run is 1. This triangle, you don't have to draw this triangle, I'm just telling you that this is your guiding line. This triangle which you have here, right, is having gradient of 1.5, and when you use your set square and whatever, right, put your set square here, okay, once it's flush, this set square is flush to this side, okay, once it's flush, you apply pressure here. You see my left hand apply pressure, this one, you can slide, and can you see that it exactly overlap this line here? So this is the most accurate tangent you can draw. You draw this tangent, that's the most accurate tangent because you're working backwards. Oh, sorry, I think this one moved a bit. It's not, but it should be. It should be. Okay, now what do you do after that? You choose any 2 points. Okay, so this is the working now. This is the working that you need to do now. You write M here. Just now, all this working is your personal working to get the correct answer. Okay, so you can erase it lah. Wherever you have written it on your paper, right, erase it. You don't let the marker mark this, otherwise the marker will know what you're up to. Okay, then this is what you need to show them. You choose any 2 points, and of course, just now I mentioned what? Choose this point, 1, 2. So you say using points 1, 2, which is the point that they ask you to find the gradient at a curve. All right. And one other point, so this point is good. All right, just now it's the same point, just now the one that I did earlier, 2, 3.5. Then you work it out, y1 minus y2, then x1 minus x2, then you get the answer. Okay, 1.50. It's exactly 1.5. In this case, there's no 3SF. All right, but if there is a 3SF, which in most cases is, then you just round it off to 3SF. This is a textbook example, so they made it very simple. Okay, now most of the time it will be 3SF. Okay, I hope that clarifies this section on gradient of a curve. So we have done sketching, we have done gradient of a curve. Okay, right now we're going to do real life application. Let me see how much time we have left. Okay, we have 54 minutes have gone past. Okay, we are more or less on schedule. Okay, now the next thing I want to go through is this thing. It's a very common sense thing. Now, another kind of questions are the last kind already. Okay, we're doing real life applications, but it's divided into this broad category of speed, time, distance, time, acceleration, time graph, and also under real life application, what are the shape of the graph you can actually draw based on the story given or the context given. Okay, now, so you have let's say one container, okay, then you pour water in, pour water in. They want to know if you pour water in, okay, at a constant rate, how fast will the height of the water in the container rise? As time passes by, right, how will the height change? will the graph look like that? If you draw the graph like that, you are trying to tell the marker that, oh, as time passes by, the height remains the same. Okay, so definitely this is not the answer. Okay, so you think about it. Originally, always start with initial condition. Remember your AMAT's exponential graph, application of exponential graph. When t equals to 0, is there any water here? No, right? So this should be the starting point. Okay, and as you pour water in, the water level will rise up constantly, because if you look at the base, the cross section of the base is uniform. It's always this circle. They fill up this circle, then go up, go up, go up, go up, go up like that. So it's uniform. We call this uniform cross section. So when it's uniform cross section, right, the graph will be a straight line. Okay, it doesn't look like a straight line, but it is a straight line. My straight line is, I don't, never mind, I use a ruler. It's a straight line, okay? Until, of course, it won't burst through, sorry, it should not go through. It will stop at a certain time. Okay, so this is how it looks like. So when they ask you to draw a sketch, you need to use a ruler. You cannot use freehand. If you use freehand, like me just now, I can say that, oh, this is not a straight line, then I mark you wrong. So use a ruler. Okay, you will understand better when I do speed time graph later. Certain parts of the graph is a curve, certain part is a straight line, certain part is a curve. So if you don't use a ruler for this part, we will think that you are drawing a curve and we mark you wrong. Okay, so be very careful on that. Okay, so this is how it looks like. I think this is quite easy to understand. If you don't understand, please let me know. Okay, now let's take a look at this second one, which looks more complicated. Let me cover up the rest. Okay, now think about it. Is this a uniform cross section? It is uniform from here, the base, all the way to here. But then after that, right, it became a smaller cross section, but still uniform. Okay, so do you agree that, or rather, which height will go up faster when I pour water in constantly? There's a hole here, there's a hole here. When I pour in water, right, do you think it will take a longer time to fill the water in this here big container or the small one? No answer. Okay, never mind. I answer myself. This, don't know whether you agree or not. This will be, let's say, constant. Something like this, constant. Okay. After that, my question to you is, will the graph become like that or like that? Will it be a steeper gradient or a gentler gradient? Okay, steeper or gentler? It has to be steeper. Okay, sorry, again, use a ruler. Use a ruler. And stop here, stop here. Stop. No, sorry, up here, sorry. Sorry, I draw on me. Sorry, your sketch, right, must match the height, the height here. So at first it is like that. Okay, then after that, it must become faster. Faster. Okay, it must become faster. Correct. Steeper gradient. Steeper gradient means the rate is faster. Faster. This is slower. But both are constant rate. Constant rate. Alright, I hope you understand. Now, how about this? Oh, it's the reverse. It's the reverse. Means at first, when you pour in water, right? Pour in water. Wow, this part fills up very fast. But then when he reaches this part, oh, slow down already because he has more space to feel, right? So it's very common sense, very common sense. Which means this part will be fast. In a shorter time, wow, very fast, it will fill up. But then this part, right, will be a gentler slope. Oh, sorry, it's again I missed it. Here, until here, okay. This is important, where the checkpoints are, okay, because the height is until here only, okay. This will be gentler until here. Yeah, so I think you get the idea lah. If it's faster, it'll be like a steeper line. Gentler, then it's going slower, which is the same which is the case here. Faster, slower. Okay, this is slower or longer time, then this one is faster. The height rises faster lah. Okay, now let's go to the next one. How about this? Oh, this one is slightly different. This is quite different, So how do we do it? As I pour in water. By the way, is the cross section, the area, cross-sectional area, uniform. Uniform means always the same, always the same. Just now, always the same, right? But now is it? No, now it's getting bigger and bigger and bigger and bigger, right? Okay, so now, maybe you think of it this way, if it is constant, then it'll be like that, right? It'll be a straight line, right? Constant, then it's a straight line, constant, it's a straight line, constant, straight line, constant, straight line, If it's constant, it'll be a straight line. But now, is your height increasing, taking a longer time to increase or taking a shorter time to increase? It will take a longer time to increase, right? So it will be a curve like that. What's going on? Okay, I repeat. If it is constant, if it's like that, if this container is like that. Oh, if it's like that, right? Then it will be this pencil marking here, straight line. Because I'll take the same amount of time to fill in this part, this circle here, consider it as different circles, cross section. I'll take the same time. Let's say 1 second, I fill up 1 cm, 1 second, I fill up another 1 cm, so it'll be constant like that. Okay, but right now, because the container is becoming bigger and bigger as the water goes in, I have more and more and more to fill. So the height will increase at a slower rate. So if you think in terms of gradient of a curve, I don't have a ruler. You see, this speed, height over time, actually is distance over time, right? If I find the gradient of this is rise over run, right? Isn't it distance over time? So actually it's the speed. If the cross section is uniform, then it will be constant speed, something you learn in physics. But if the cross section is becoming bigger and bigger and bigger and bigger, then your speed will be decreasing, right? Or slower. Okay, so do you agree that the gradient of the curve here will be gentler? At each point, right, my speed is slower. Okay, so that's why the graph is this way. Alright, I hope you are clear. Now let's go to the next case, which is the reverse case. Imagine I turn this around, then there's a hole here, and then I fill in, right? At first, it takes a long time. Okay, wait. At first, it takes a long time to fill up. Then as it gets higher and higher and higher, the speed gets faster, right? Okay, so how do I do it? Now, you think of it this way. If it's a constant thing, if it's a constant speed, it'll be like that. But it is not constant. Is it getting slower and slower and slower? Is it getting slower and slower and slower? Slower and slower and slower. Then it'll be a curve that is bending away from this constant. This is constant. But it's not. The height will be increased faster and faster and faster. So the correct graph to draw is like that. Meaning to say that if you were to find the gradient here, gradient here, gradient here, gradient here, gradient here, gradient here, you find that the gradient, can you see my this template here? The gradient of the slope is increasing, getting faster and faster and faster and faster and faster. How about here? For this uniform shape, gradient everywhere you learn in physics is the same. Okay, it's the same what? The time taken to fill up here, fill up here, fill up here is the same. How about this last, the previous question? Gentler, gentle, 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 smaller, less. Yeah, taking longer time. Okay, so just remember this. Sorry. Go at this part. If the speed is constant, please use a ruler. Constant speed is like that. When it's getting slower and slower and slower, then it has to be, of course, below this constant speed lah. Slower and slower. Just remember this is very simple. And it's getting faster and faster and faster. You see, the gradient at each point is increasing. Yeah, so that is the main thing you need to know for this kind of questions. Okay, now that you know this, let's take a look at this question. This question is divided into two parts. Alright, so you need to draw this dotted line here. Just now also you see, when the container is divided into two parts, right, you need to draw a dotted line. But most of the time, the question in the exam, they will actually draw for you. They're very nice. They will draw for you, okay, to tell you that, hey, you need to take note. The rate of increase here, or the rate of decrease, or whatever, is different for this part and this part. So now you think about it. This part, it takes a long time, right? So it's slow, right? Then later, faster, you fill up faster, right? Which means that the first part is not constant. If it's constant, it's like that. It will get faster and faster and faster and faster. So it will be faster and faster and faster and faster and faster and faster, like that. Correct. If it's slower and slower and slower, so then you bend away now. Okay, now what happens here now? At this part here, you have entered another shape already, and this shape will get slower and slower and slower. This one is faster and faster and faster. That's why it bend upwards. Bend upwards. Now it gets slower and slower and slower. Okay, if this shape had been like that, right? It had been like that. That means this line, if it had been like that, right, the gradient here will just be a straight line from where this part is, something like a projectile like that. Shoot straight. Whatever this gradient here is, I will shoot straight and follow. If the shape is like that, because the rate of increase here is the same as all the rest, because it's uniform, just like your very first case here. Okay, but in our example, it is not. It's becoming slower and slower and slower. So slower and slower and slower means you bend away from this constant line. So this is your, let's say this is your top. So you bend away, and this is what you get. It's a bit off, but that's the idea. So this is how you should draw the sketch. Alright, now we just do one more. How about this? Again, this is height in cm, and then this is time. So as time passes by, what happens? This is uniform, which means that it must be a straight line. Okay, it must be a straight line. Let's say I draw that. I have to stop here, right? Because this is where the container ends. I have to draw this dotted line here. Okay, now after this, it gets longer, slower and slower the rate of increase of the height is slower and slower and slower. If it's constant, you go like that. If it's constant, you go a straight line. But now because it's slower and slower and slower, so you go and draw this until you reach this opening here. Alright, so I hope you are clear. I think it's pretty straightforward lah, but certain things you may need to look at it. Okay, so you may want to copy this and then you go and figure it out yourself, or later we will try some of the questions. Okay, so now we're at the last part already. We're at the last part of this chapter. Once we finish this, we are done. Okay, now you may have learned this. I think you would have learned this already. It's the first few chapters in your physics. Now, if you have a distance time graph, then you have this straight line here. Now, what is the gradient of this line here? What does it represent? It represents, in mathematics, it's the rise over the run, right? Rise over the run. So it's actually distance divided by time. Actually, just now I mentioned before in one of the questions earlier. Distance over time actually is speed. Oh, that means what I'm trying to tell you, right, is the gradient of a distance time graph is speed. That's all. Meaning to say that, let's say this is 10 meter, this is 2 seconds. So if I ask you, hey, hello, what is the speed this fella is traveling? Then you'll be 10 over 2, which is 5 meter per second. If you want, you can use your physics formula. You can use that. It's the same thing. Okay, but be very careful of the signs and read the question carefully. Okay, how about this? What is the gradient of this speed time graph? Speed time graph, you take the speed over time. In physics, you learn that it's the rate of change of speed, so you get acceleration. Okay, which is in meter per second square. Actually, from the units you know already, this is meter per second. Alright, divided by second, so it is 1 over s, so it's meter per second square, correct? Whereas this is meter over second, so it's speed. So the units can tell you a lot. Next time in the university, you will learn this not in JC you learn already this thing called dimensions. You will know all this already. Okay, how about this? This we won't discuss. Okay, I'm just trying to tell you that from here you can go to here. Okay, I think this is quite straightforward. Now the next thing is probably slightly more challenging for some of you. So do ask me if you have any questions later. Now let's take a look again. In exam questions, they like to make you move from distance time graph to speed time, and then sometimes from here to here, sometimes from here to here, here to here. So you have to be able to work forward and work backwards. Okay, so this is what I'm trying to, the skill that I'm trying to go through with you now. If you have a graph like that, which describes the movement of particle or whatever, okay, at first it is going a curve here, then this is a straight line, and then this is a curve again, then this is a straight line. So just now I mentioned, right, it's very important to use a ruler, okay, because in the exam you don't use a ruler, we may think of it as a curve. Now, what am I trying to ask you here? Okay, first of all, the gradient of a distance time graph we mentioned just now is speed. Okay, represents speed. Alright. Now, if I want you now to somehow from this graph convert it into a speed time graph, would you be able to do so? Okay, don't worry about the values, we just know the shape. Now, let's take a look. If I were to look at this part, okay, let's call this O, A, B, C, and then this one D, okay? From O to A, what's happening? O to A, what's happening? O to A, what the distance is, what's going on? let's study more about the distance time graph. Okay, although you might have done this in physics, just to make sure. When a distance time graph is like that, what does it mean? Oh, that means, let's say this is 10 meters. The person is stationary, right? Stationary. Then when it's like that, oh, the person is moving back towards probably the starting point, O. Okay. Then when it is like that, oh, it has reached the original point. So that is a distance time graph, right? Now, what about this? What is the person doing? If I were to draw the, sorry, again, this is a straight line. If I were to draw the graph like that, right, what does it mean? It means that the person is moving at, okay, simple, constant speed, correct? Constant speed. Because when I find the gradient of this, it's just 3 divided by 3, I will have 3 divided by 3 is 1. Yeah, I will have the speed for the first 3 seconds is 1. It's a straight line. Alright, constant speed, right? Yeah. Then if I were to put it, from 3 to 6, I put a horizontal line for distance time graph. Okay, you very importantly have to see what graph this is. Is it distance time or speed time? Okay, if it's a horizontal line for distance time graph, then what's going on? From t equal 3 to 6 seconds, it is stationary, right? Stationary. Okay, so if it's stationary, what is the speed? It is 0. It is 0. Okay, immediately 0. He stopped maybe buy something or talk to a friend or whatever. Okay, now what if it is just now what was the case? What if it is like that? Okay, now that's why just now we learned this. Okay, you may not be able to see, but it's called gradient of a curve, right? That's why we learned this just now. It's very important. If I were to find a gradient here, find a gradient here, or find a gradient here, or find a gradient here, can you see that my slope is getting steeper and steeper and steeper and steeper. Okay, meaning my gradient getting higher and higher and higher. And if my gradient is getting higher and higher and higher, it means that my speed is getting faster and faster and faster, greater and greater and greater, correct? So, what does this mean? It means that it is increasing. Is it? Okay? So we keep this simple. We assume that it is constant rate, increasing at a constant rate. Alright, so this is what is going on here. Okay, so if I were to ask you to transform this part here into here, it will look, I draw dotted lines. It's very important that you understand what these dotted lines are for. Let's say this is a 5, 10, 15, 20. Okay, this represents different timings and different sections of the motion of the person. Alright, so for this first 5 seconds, like that. This one, what is going on here? It's a straight line. If I were to find the gradient here, gradient here, gradient here, gradient here, it's all the same. I find gradient here, anywhere on this straight line, right? The gradient is the same. So, constant speed. Let's say it is, I don't know, 5 meters per second. Like that. Okay? So it becomes a straight line. How about this? This curve, this is a curve this way. Just now it was a curve like that, getting faster and faster and faster. So this must be getting slower and slower and slower, right? Getting slower and slower and slower means What does it mean? It means, let's say down here, at this point here, this very end here, if I were to ask you to find the gradient at this point here, it will be the speed, right? And the value will be 5, right? But if I ask you to find a little bit further, oh, then it'll be less than 5. Even less, 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 until you become a horizontal line, and that's when the speed is 0. So it'll be like that. And then for the next part here, because he's stationary, stationary, it'll be like that. Okay? Yeah, so this is what I need you to know to be able to move from here to here, and then for certain questions, here to here. Okay? Now, again, just to emphasize, the gradient of a speed time graph is acceleration. I think we won't do this. We'll do this another time. Yeah, we will now go to this book. Remember, beginning of this thing? Did I pass you this book? Oh, I think, sorry, it's not this book. But you would have a question, something like that in your own TYS, the one that was given to you free. If you have it, you take a look. If not, then don't worry. I have the question here. I am doing November 13. Can you see? November 13, paper 1, question 24. Okay, but never mind. You just refer to this question here. It's the same as the one in your book. Okay, I think this is the one. Yeah. Okay. Now, let's say you're given a question like this. Let me see what's the time. Oh, 1 hour 20 minutes. Okay, I will be ending soon. You're given this speed time graph. Okay, speed time graph. Time, speed in meter per second, time in seconds. Now this is a real O-level question. Now, so you see how easy it is, okay? Calculate the acceleration of the car after 5 seconds. Oh, acceleration. How to find acceleration? Acceleration, you notice this is a speed time graph. So if I were to take the rise over the run, it will be speed over time, which is meter per second divided by, meter per second divided by second. So it will be, so it is actually acceleration. So all I need to do is to find the gradient of this speed time graph. Okay, now they want 5 seconds, but there's no 5 seconds here, but you know that probably is somewhere here. Okay, but it doesn't matter because we mentioned what? Gradient of any point on the straight line is the same. Even if I say 1 second, 2, 3, 4, 9.9, 9.999 is the same answer. Okay, anywhere here is the same. So what do? I just take 16 divided by 10, so it's 1.6 meter per second square. Correct or not? Okay. Check the units. The units must match. Okay, because sometimes they give you what you call that, kilometer per minute, then now here is in hours. Then you need to do the conversion on your own. Okay, now calculate the total distance traveled between the two road junctions. Now how to find distance? We didn't discuss this just now, but I think it's common sense. How to find distance? You learn in not too long ago, maybe kindergarten. You learn total distance between the two road junction. Where's the two road junction? Is between here and here, right? Okay, you learn that distance is speed times time. Correct? Isn't this speed and isn't this time? Okay, meaning that this is time, this is speed. You find this area, you will be able to get the answer already. I think you learned this in physics, so I won't belabor the point too much. So you take half times this, that will give me 80. This part is 80. You can actually use half A plus B times 16, which is the area of trapezium. This is a trapezium, right? But you will see later why I want to break them up into parts. Because later you need to sketch a graph. Okay, so I want to break them into parts. This part here is 80. This part here is 10 times 16. Be very careful. It's not 20 times 16. It's 10 times 16. So it's 160. Wait, let's see whether you can see. Yeah, you can see. Okay, the last part is 15 times 16. 15 times 16 is what? That's terrible. What is 15 times 16? 120, sorry, 120. That's terrible. Okay, 2. So you know this the total distance will be, you add them together, 360. You show the necessary working, all right? 360 meter. Okay, so that's for the first part. Okay, now the next part. I just show you what the question says. Use the grid below. Okay, so I've drawn for you already. This was the diagram you saw earlier. They say use the grid below to sketch the distance time graph for the journey. So I think I better use this, then it's clearer to you. Okay. Yeah, I think you can see. Now, I will put this here. This diagram was from the previous page. Okay, everybody can see. Use the grid below to sketch the distance time graph. Notice that this is speed time, they want distance time graph. And just now we have found that this is 80, this is 120, right? And this is 160. Okay, so how do I, from this speed time graph, sketch a distance time graph? Okay, so I mentioned to you just now, the checkpoints are very important. You know, you need to know that you need to have a checkpoint here. Okay, that means the shape of the graph here may be different from the shape of the graph. Okay, don't do like what I do. I'm just showing you that the shape of the graph here may not be the same as the shape of the graph here. Normally it's not, and may not be the same as the shape of the graph here, okay? Because these are different checkpoints. And of course, your ending point is not 40, but 35. So you have to know this. Okay, now let's do the question. Distance traveled. Now, do you agree that the first 10 seconds, in the first 10 seconds, the person actually traveled 80 meters? Here. That means in 10 seconds, the distance traveled is 80, so your ending point is here. Okay, now how about the next stage? The next stage is 160. 160 is in addition to this 80, you know. That means here to the 20th second. 20. Oh, sorry, I wrote wrongly. Okay, so it is 20, right? Let me check. Yeah, 20, sorry. 20, so the checkpoint should be here. Okay, don't do like what I do. I'm just showing you. So 1 part, 2 parts, 3 parts of the graph. Okay, now, at the 20th second, it would have traveled this plus this, 240. 240, so this is the other important point. Now the last one, this plus this plus this. Just now we calculated already, it was 360, right? 360, where is 360? Okay, now how do we draw this graph? Now you know already that something happened here, then you reach here, something happened here, then you reach here, something happened here, then you reach here. So now we are trying to determine whether it's a straight line, whether it's a straight line, whether it is like that, getting slower and slower and slower, slower and slower, or getting faster and faster and faster, or constant speed. Okay, something like that, right? Okay, something like that. Okay, now from 0 to 10, what's going on? Is your speed increasing? Okay, if your speed is increasing, how should you draw the graph? Should you draw How should you draw the graph? Can you think about it for a while? Would it be like that? Speed increasing, so would it be like that? And then this has to be a straight line. And then this is like that. Okay, is it like that? Alright, you go and think about it, okay? We have done a lot just now already. Compare this with this, compare this. Actually, I wanted to draw it this way to show you, but never mind. We use the grid. The speed is increasing here, correct? Whereas the speed is uniform here. The speed is decreasing here. So, how do we know whether what we have drawn is correct? Okay, it is normally easier to go from this distance time graph to this speed time graph. Here to here. The other way, from this to this is normally tougher for us normal human beings. Those not so normal one, they have no problem. Okay, so let's see. If I were to draw this, is it correct or not? Let's think. Let's say I find gradient here. I find gradient here. I find gradient here. Is it increasing? Is it increasing? Yes. The speed, because the gradient of a distance time graph, right, is speed, right? Speed here, I get more, get more, get more, get more, then get more, 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 like that, right? Then down here, right? Down here, whichever point I choose, I find the gradient here, right? I find the gradient here, gradient, any point here, the gradient is the same. Okay? Because when I find the gradient here, let's say it's 16, right? It will forever be 16 from this point all the way to this point. So this part is correct. Okay? Now how about this part here? Think from here, think from here, not from here. It is easier to think from here. I find the gradient here, it will have to be 16, right? Somewhere here 16 then, but it will decrease 16, then maybe 15, 14, 13, whatever, and then becomes slowly becomes 0. So this is the way. Okay? Now let's see whether I have time to do. Oh, time's up, 1 hour 30 minutes already. So I actually have a few more examples. Never mind, we will do next lesson. For today, your homework will be there's this pop quiz on what do you call that? Sketching of graph. Can you do that first? If you want to start on the homework, you can start on the homework. Alright. I will send you the answers for the pop quiz and the homework over the next few days. Alright. The other pop quizzes, I think if you want to do, you do. You don't want to do, then we wait for the right time to do. Okay, thank you.